All right, guys. In this video, I'm just going over kind of one of the last days we have to review for the final exam and the AP exam. And since our Blue Day class doesn't get has one less day to review, I wanted to make a video of this because we might not have time in class in eighth period to go through all this. We will in seventh period, but not necessarily eighth period. So the Orange Day classes kind of have an advantage, just with how much more class time they have for a review. So you're getting this, eighth period students. You're getting this packet, but we might not have time to get through all the explanations. So I'm just making this video to explain those things. So again, it's just going over some free response AP questions and just looking at different kind of things to look out for, mistakes not to make, and the focus here is just kind of the different lab stuff that you need to be able to talk about. And maybe I just want to review a few things too. So I just picked these free response questions just to highlight some things, okay? So the first one here is looking at chromatography, because we really don't talk chromatography in AP chemistry. So I just want to review it. If you get a chromatography question, it's basically, is the color of the dye, or is the dye polar or nonpolar? Is the chromatography paper polar or nonpolar? And then is the solvent polar or nonpolar? So you can see chromatography questions are basically just going to be understanding that like dissolves like mixes with like interacts with like. So polar will interact with polar and nonpolar will interact with nonpolar. And so right here we're told we have a nonpolar solvent. So the liquid here is nonpolar. Okay, and then if we look at the question, it says the paper is polar. So we know the paper is polar and the solvent is nonpolar. So what's going to happen in chromatography is you're going to dip the paper into the solvent. The solvent's going to start to go up the paper, via capillary action, and as it goes through the paper and it goes through the ink dots, the ink is going to travel with the solvent up the paper, but the distance it travels is going to depend on how much it interacts with the paper versus how much it's interacting with the solvent. So if it interacts with the solvent more, it's going to travel with the solvent further. If it interacts with the paper more, it's going to not travel as far. And so since the solvent is nonpolar, whatever is most nonpolar will travel the furthest, and whatever is most polar will travel the least distance here, because the paper is polar. So it's going to stay where it is with the paper and not really go with the nonpolar solvent. Okay, but the opposite could be true if it was nonpolar paper and a polar solvent, but that's kind of the idea in this question. Okay, so for part A, it's just asking which of the dyes, A, B, or C, is the least polar. Well, the least polar would be the one that moved the furthest, and dye C moved the furthest. And since the solvent is nonpolar, that would make dye C the least polar, or the most nonpolar, because it mixed with the nonpolar solvent the best, basically. Okay. And then the second question is which dye is present in the unknown sample. So we have dye A, B, and C after they were dipped into the solvent and went with the solvent on the chromatography paper, and this is what the unknown did. So what you don't want to do is say, oh, it looks like it's at the same level as B. It's really not about how far it moved compared to how far these moved. It's really what is the ratio between the starting point and the ending point of the solvent. So the end point of the solvent is called the solvent front, and then you have where it started, or the origin. So dye A is kind of halfway between the starting point and the solvent front, and the unknown is halfway. On this piece of paper, it's halfway between the starting point and the solvent front. So we would expect this unknown dye to be die A, okay? And I gave you the scoring guide for it so you can read how they kind of said it, but the way I explained it would be more than enough for credit there. And that's really, think of a chromatography question as more of like a like mixes with like question. So it's really, comes down to polar versus non-polar and that kind of thing. All right? Okay. The next couple questions are the past 2 years on the AP exam, they've given you some kind of blank space and ask you to kind of write out either the full lab procedure or some missing parts of the lab procedure. And so a couple things here. This is how we could make a buffer solution. And it explains, like, so what you would kind of have to know here is, notice they give you this and this. So you might be going, asking yourself, well, okay, well, wait a minute. I need a weak base and its conjugate acid, or a conjugate acid and its weak base. So what we'd have to understand is this paired up with chloride, if you took the chloride off, that would be the conjugate acid of CH3NH2, okay? So the thing about the lab procedure, whenever you're going to weigh out something, make sure you say you use the weigh paper and the balance to measure the mass that you want. Or sometimes it might say a weigh boat, okay? Just don't place the solid that you're taking the mass on directly on the balance. You use weigh paper or a weigh boat. So that's kind of something to note. And then remember, whenever you're using a burette or a graduated cylinder or something, or maybe it's a cuvette question, if the initial rinse of that glassware is with distilled water, before you do anything with it, and before you totally use it to measure an amount of the other liquid you're trying to measure, you want to make sure you do an initial rinse of the burette, or the initial rinse of the cuvette, or the initial rinse of the graduated cylinder with the solution you're trying to measure. So, because if you don't, right, the droplets of water from the washing of distilled water will dilute the solution you load into it. So you want to rinse it with the solution and then measure it and then fill it up, okay? So in this question, okay, again, they give us weigh paper. It looks like we're measuring the mass of the solid. They kind of gave us that already. But notice, though, in this year's exam, this was, I think, 2 years ago, and this one was last year's exam. 2 years ago, they gave us this, and, they said use the weigh paper. Okay, that's great. Remember, we're using our volumetric flask here. It's 200 mils, okay? And here we would, use the weighing paper to measure the determined mass of silver nitrate. We have to get that into the volumetric flask, rinse the weigh paper or the weigh boat with distilled water to ensure all the solid gets into the flask, and then fill it to the line with distilled water to make your solution. And then you might want to say, like, once all the salt's dissolved, shake up your solution a little bit, stuff like that, okay? All right. Here, this question I just kind of threw up there because, in this part of the question, they're asking you to measure 10 milliliters of Fe2 plus. You want to deliver 10 milliliters. And in part F, they're just asking you, why wouldn't you use a volumetric flask? Why would that be a bad thing? Remember, a volumetric flask can only measure one volume. So a volumetric flask can measure 25 milliliters if it's a 25 milliliter volumetric flask, right? You could use a graduated cylinder, but in this case, if you wanted to deliver 10 milliliters of something, the best one would be to use the burette, because the burette would go to 2 decimal places on your measurement, whereas a 25 milliliter graduated cylinder would really only go to 1 decimal place. And remember, a volumetric flask can only measure 1 volume, okay? Here, I just wanted to bring up, when you take a measurement, to understand that you need an estimated digit. So here, if it's a burette, make note, look, this is 3, this is 4, so each tick mark represents 0.1 milliliters, so you're allowed to estimate to the hundredths place. So this measurement needs to be the hundredths place. This measurement needs to be into the hundredths place. And remember, when you do final minus initial, you're limited by decimal places, not sig digs. So if this measurement has 2 decimal places and this measurement has 2 decimal places, then when I subtract, I should have 2 decimal places. So let me show you how this could be a little tricky. So remember, burets read backwards. Like a lot of people might misinterpret this as 4 point something, where it's really 3 point something. It's 3, 3.1, 3.2, 3.3, and here's 4. Okay, so here I said 3.35. Now, if you said 3.36, you're correct. If you said 3.34 or whatever, if your estimated digit is different than mine, that's fine, but you need to have taken it. If you just said 3.3, no, that doesn't work. Okay, and then here I said 29.55. Here I said 33.5. Now, most people probably would make both those estimates because the meniscus looks kind of like right in the middle, so 0.35 here and 0.55 here. But when I subtract, notice my calculator, if I did my calculator, it says 26.2, but I need to make sure I report 26.20 there, okay? But don't always think you always have to go to 2 decimal places, because let me show you another question. I'll come back to the Beer's Law question. Where did I have it? I thought I had another one. I guess not. Okay. There was another question where the tick marks went up by 1 milliliter, so you were allowed the 10th place. So remember, if each tick mark represents 1 milliliter, then you estimate to the 10th place. But if each tick mark represents 0.1 milliliters, you estimate to the 100th place. So you got to make sure you take a proper measurement, okay? All right, so here we got an absorbance versus concentration graph. So remember, the slope of that line, if we calculate the slope, would be the molar absorptivity constant. And if we were using Beer's Law, A equals ABC, that would be the lowercase a, or the epsilon symbol, which is the molar absorptivity. So the slope of this line would give us that. Now, the reason I brought up this question is because it's saying, this is the student's procedure here, and it's saying what might have been something the student did incorrectly to result in this data point here. So notice it's not this solution with this concentration is not absorbing as much light as it should based on our graph. So what we need to understand is that means a lower absorbance would mean it's less concentrated than it actually should be. So it's like, which of these steps might have the student done something wrong to result in a lower concentration for this reading of the cuvette, or this absorbance reading, okay? And I think the main reason would be if you forgot to do that initial rinse with the stock solution as opposed to just distilled water. If you rinse the cuvette with distilled water and then you immediately load it with your solution without rinsing it with the solution first, now that solution that's inside the cuvette is going to be a little bit more dilute than what it should be. And so since it's more dilute, it'll absorb less light and you would get a lower absorbance reading. So I think that would probably be the best reason, or probably the most likely reason why this one didn't. They forgot to do that rinse with the standard solution. They just did the rinse with the distilled water. Okay. Here, I just wanted to throw out here, we got a galvanic cell. The key thing you should be seeing that's missing is you don't have a salt bridge, right? So the reaction's not going to work here unless you have a salt bridge, okay? And then just a couple of things, just to make note, just to review some electro stuff. If we look at, this has 1 electron, this has 3 electrons. So when we do have the full balanced redox reaction, it'll be 3 moles of electrons transferred. So when we're solving for delta G here, where we're saying delta G equals negative NF potential, N would be 3, okay? So just making note of that. And then be careful here, right? This is a reduction potential, this is a reduction potential. One of these has to be flipped and be an oxidation potential, but this question mark is asking what is the reduction potential of chromium 3 plus being reduced to chromium. Okay, so in the question they tell us silver is reduced. So this reaction is going to stay as it is. This reaction is going to be flipped. And so if we use the standard cell potential that they gave us, and we say the standard cell potential equals the reduction potential, which is 0.8 because we were told silver is reduced, plus EOX. When we solve for EOX, that number is going to be the potential for the reverse of this reaction. So that comes out to be 0.74, meaning the question mark value here would actually be negative 0.74 because they wanted the reduction potential. And this is the oxidation potential of chromium being oxidized to chromium 3 plus. That's what the positive 0.74 represents. So that question mark is the negative 0.74 volts that they're looking for. Okay. All right. Here I just want to review kind of a KSP equilibrium, but KSP equilibrium. Okay. So first off, they ask us the hybridization of the oxalate, the carbons in the oxalate ion. Well, they gave us the structure. You got 3 bonding domains, 0 lone pair domains, so a total of 3 domains around each carbon. So remember, hybridization, just memorize. 2 domains is sp, 3 domains is sp2. If there had been 4 domains around each carbon atom, it would be sp3. Okay, so 3 domains, sp2. All right. Now they ask us to write the KSP expression for the salt silver oxalate. Notice the subscript of 2 for the silver. So we didn't have to write the reaction, but when this salt dissolves in water, you get 2 silver ions, you get 1 chlorate ion. So the KSP expression would be for this reaction. Remember, this is a solid, so it's not included. So it'd be KSP equals the silver concentration squared times the oxalate concentration. Okay. Here they just ask for the molar solubility. So we can use our solubility shortcut because we have a 1 to 2 ion ratio. We can say KSP equals 4x cubed. Remember, in these shortcuts, the KSP shortcuts, X is the molar solubility, KSP is the solubility product, which was given to us here. So we would plug in the 5.4 times 10 to the negative 12 over for KSP. We'd solve for X. X is the molar solubility. When you solve for molar solubility, remember, it has units. It's moles per liter. It's molarity. Now, if they went one step further and asked for the silver concentration, this is where we'd have to be careful. The silver concentration would be this number times 2. The oxalate concentration would be this number. This molarity, the molar solubility, represents the moles per liter of the entire compound. So if you want the molarity of the specific ions, you would take the molar solubility and multiply by the subscript of that ion. So this times 2 would be the silver concentration. This times 1 would be the oxalate concentration. Okay. Now, part 3 of this question is a little bit tricky, and it takes a lot of kind of background knowledge that we should have, but we got to be able to apply it. So it's asking why does silver oxalate become more soluble in the presence of perchloric acid? So the first thing to recognize is this is a strong acid. So really it's asking why, when the solution's acidic, why when there's a lot of H plus in solution, does this become more soluble? Okay, why is it more acidic in an acidic solution? Or why is it more soluble in an acidic solution? And the reason that is because if H plus combines with oxalate, you get a weak acid, and the weak acid will stay together. It's because oxalate is the conjugate base of a weak acid. And so the excess H plus will take out the oxalate, and then more oxalate will have to dissolve, more silver oxalate will have to dissolve to reach the point of saturation. So there's 2 ways you could say it. You could say H plus and an oxalate give you HC2O4 minus, or you could have said 2 H pluses and an oxalate give you oxalic acid, H2C2O4. Okay, but that's the reaction that's happening. That's taking out the oxalate ion, so it's lowering this concentration, causing this process to shift to the right, meaning more of the solid has to dissolve, meaning the salt is becoming more soluble. Now, again, 3, that's a tough question. I don't know if a lot of you would have gotten this one. But look, it's question 7, 1 prompt, 2 prompt, 3 prompt, 4 prompt. So this is only worth 1 point. Okay? This was an easy question. This was an easy question. This was an easy question. We got 3 out of 4 points. We're at a 75%. That's definitely good enough for a 4, maybe a 5. So just again, you're not going to get all the questions right, but remember, this question is only worth 1. Okay, so it is the last question of this test, but it's also, only worth 1 point. Okay, so a lot of students aren't even going to get to this question on the exam, but even if you did and you didn't get it, okay, it's 1 point. Okay. Right here, I just got to review partial pressure just because we've kind of talked about that a couple times so far, and I want to make sure we got it. So here, they give us the total pressure, and based on the diagram, they want us to find the partial pressure of the CO. So the first thing to do would be to count the total particles. There's 10 particles, and then count the amount of CO. There's 3 COs. So 3 divided by 10 times the total pressure will give us our partial pressure. So that's the mole fraction times the total pressure gives us the partial pressure. And then I didn't have the full equation because I only printed off this part of the question, but this reaction was given to you at the beginning of the question. So this gas yields this gas plus 2 of those gases. So write the equilibrium expression Kp for this reaction. Remember, it's products over reactants, but that coefficient has to become my exponent, and we use partial pressure notation, not bracket notation. Bracket is for molarity. Okay. And then here I just wanted to review a couple dot structures. I think I saw Mr. Denny doing this example in the rapid review video of the day. So I won't spend too much time, but just remember, you need at least 1 bond between all of the elements. So that's, throwing the bonds. Hydrogen can only have 1 bond. So once you draw that line there, that part of the drawing's done. You should add up the overall number of electrons needed. It was 1 plus 6 plus 5 plus 6, so 18 electrons. If we draw single bonds and then we add lone pairs to the must-have 8s, we have 18 electrons here, but the reason why it's not right yet is nitrogen doesn't have 8 yet, so we have to make one of those lone pairs a double bond. So there would be kind of the final structure there, okay? And then here's another one. Again, they gave us the chlorine, the sulfur, and the chlorine all right next to each other. So the first thing I'm going to do is draw single bonds between them. They might turn into double bonds. They might turn into triple bonds, but that's the first thing I'm going to do. At least 1 single bond between them. And then, again, I want to know how many total electrons, in this case 26. So if we just start adding lone pairs until we get to 26, let's see what happens. So we got 2, 4, 6, okay? And then we would go... So 2, 4, 6, then we would go 8, 10, 12, 14, 16, 18, 20, 2, 4, 6. So adding those lone pairs make us have 26 electrons. Chlorine has 8, sulfur has 8, that sulfur has 8, that chlorine has 8, so no reason for double bonds. We're not worried about formal charge or anything. They're not asking like which one's better than the other one, that kind of thing. But now they're asking about bond angles. Remember, this bond angle is not 180. 109, 4 domains say 109. You could say 105 if you want to because it's bent, okay? But be careful with that. They drew them straight across on purpose to make you say 180 when you get to this question. Okay, so again, I just made this video going over some of the free response that you have. And I made the video because 8th period might not get all the explanation that we do in 7th. Okay, so just heads up. All right, have a good day.